Okay. You don't think so as in it did not fix it or it did fix it? It did not fix it. Okay. Well, we'll just try and write on the left-hand side of the screen then today. Okay, so 3.3. 3.3 is a pretty big section, which is why we're going to spend not just 1, but 2 days on it. Okay, so we're going to have part 1 today, and we're going to have part 2 on Monday of next week. Okay, so 3.3, definitely a really fundamental section. Something that we want to feel really confident on. I know we've been focusing a lot on concepts and not so much on computation. And I will say that 3.3 is computations are important. All right, so computations have to be accurate, and the concepts that we're going to be learning are also going to be important. Okay, so sometimes folks focus a lot on just the computation, like, can I do it? And they don't think about the concept, like, how do I know when to do this? When might I use this rule versus when I might use that rule? Like, all that decision making and problem solving are still going to be incredibly important in this section. Okay. So let's start off with what we know. All right. What we know is that we talked about an average rate of change versus an instantaneous rate of change. Okay. And so that was from yesterday. We have average versus instantaneous rate of change. I saw some really good answers in the discussion about the difference between average versus instantaneous rate of change and the comparison, like what's similar versus what's different. So that would be a really good thing to read over, a really important concept to understand. And the second thing that we talked about yesterday was the formal definition of a derivative. Okay. Now, that formal definition is important to understand, like, where things come from, why it works the way it works, and to be able to use it to strengthen your algebra skills. Okay. Anyone who's taken calculus before knows that the formal definition has sort of a short-lived lifespan. And in fact, today we're going to stop using that formal definition because everything that we do from here on out is actually going to be a shortcut of that formal definition. Okay. The last thing that I actually want to include here, and I didn't write it down on purpose because I think it's important to really just highlight this last piece, which is that oftentimes I have students who say, well, calculus is really hard. They're like, I understand what we're doing, but I just can't get to the answer. And a lot of times that gets back to the fact that maybe the algebra foundation is not as strong as would be beneficial. Okay. And so some skills that we're going to continue to see that I want you to work on, depending on how well you feel like you know it. Factoring definitely will continue to come up. Conjugates will definitely continue to come up. Fractions will definitely continue to come up. Okay. So those are some, not all of the algebraic pieces that we're going to use. But if you look at any one of these, factoring, conjugates, or fractions, and you're like, I don't know how to do those, it's on you to go to the interweb and find some sources to work on those skills outside of class. Okay. If you're like, well, Judy, I looked on the internet, I'm not sure if these are good sources, or do you have any suggestions for better ones? I'm happy to help you out. So, definitely ask if you're like, I'm not really sure if this is a good resource or not. Definitely ask and see, what I can do to support you in that learning of other things to help your calculus. All right. But what's new today, we're going to be focusing on a bunch of rules, okay? Now, some of these rules are fairly straightforward. In fact, I think Vincent brought up one of those rules yesterday, okay? But some of the rules seem kind of complicated. And one thing I want us to remember here is all rules are shortcuts for the formal definition, okay? All rules that we learn from here on out are actually shortcuts for the formal definition. So if you're applying a rule and you're like, this is so long, it could be way worse is really just what I'm telling you. It could be so much worse because we could be doing it versus using the formal definition every single time. Okay, so just kind of keep that in there as a perspective that yes, the rules might be tricky, but they are saving you time and a lot more algebra than using the formal definition. Okay. And so here are the 4 rules that I hope we walk away with today feeling confident on. All right, we've got power rule, we've got sum and difference rule, we've got product rule, and we've got quotient rule. I don't think I've taken very many upper level math courses where I have not used these rules. Okay, and I mean beyond Calc 2, you use them in Calc 3, you use them in differential equations, sometimes in linear, but all these rules definitely are ones that if you learn them now and you learn them well, will definitely pay off for as many math classes as you need in the future, okay? So with that being said, let's start with the concept, all right? So we talked about the idea of the derivative yesterday. I wanna just review that really quickly. We're gonna draw a picture and we're gonna write down some notation, okay? Now, some of this notation I did throw in the Discord chat yesterday so you could kind of start to see what it looks like. And so one of the things that we will do today is also make sure we know like what all those different notations are. Okay, so let's start off with a picture because it is me and I like pictures. So a derivative is the following, okay? You have a function. It could be any function. All my functions pretty much look like this. I don't know why, but it's a function. And in this function, if I want to find a point, right? Let's say I have a point that is right here, all right? What would you tell me about the slope of that point? Positive, negative, 0? Yeah, that slope is positive, right? And so in particular, we could envision that, what is this line called again? We learned yesterday.
Tangent.
Yeah, the tangent line, right? So if I wanted to find the slope at a specific point, right? So maybe I have the blue point and I'm like, okay, that should be a positive number. Maybe I have this orange point here at the bottom. What would we say the slope is there? Ooh, 2 really important phrases here. I see a 0 and I see no slope. What are our thoughts? Which one of those is correct? Positive, or sorry, 0 or no slope? Yeah, so this blue line has a positive slope. This orange line has a 0 slope. And I think one of the things that maybe leads us sometimes to say none is that I think when we were maybe in elementary school and we had 0, we're like, well, how many is 0? We're like, none. And so we connect in our brains that 0 means none. But when we're talking about slope, it's actually really important to be really careful with our words here. So a 0 slope is actually going to be very different from an undefined slope. Okay, so if it's a horizontal line, which this is supposed to be horizontal, I'm looking at the picture now, it looks a little crooked, but it is a 0 slope or a horizontal line. Okay, and if I were to maybe throw one more point, like right over here, that green point, what would we say about the slope of that point? That would be negative. Good. And I could sort of that in, and we have a negative slope. Okay. So we can look at a curve and we can analyze the slopes at specific points, okay? But if we're gonna find the slope at a specific point, then what we wanna say is we can find the derivative of a function, right? We can find the derivative of a function and plug in our desired x value. Okay, so this concept right here, I can look at a picture, see the slope, ties very closely to this idea of derivatives, because derivatives give us a way to find the slope at specific points. Okay. Now I notice a question in the chat about how do we know that the orange one has a 0 slope. So by definition, a horizontal line has a slope of 0. Okay, so by definition, a horizontal line has a slope of 0. But additionally, if you think about slope as rise over run, if we have a horizontal line, the rise is 0. The run is forever. So 0 divided by anything will give you 0. Okay. All right. So this is sort of the concept that we're going to be working with. And no matter how complicated the computations get, and they're going to get kind of complicated, but no matter how complicated they get, all we are doing when we find a derivative is finding slope. Okay. So just keep telling yourself that no matter how bad it gets, what am I doing? I am finding slope. That is what we are doing. Okay. Now, notation is definitely something that comes up quite a bit. Okay. Meaning, how many ways can I write derivative using math symbols? Okay. So to write derivative using math symbols. Okay. All right, I see one in the chat already. So one way that we can say this is f prime of x. Okay, so one way we can say this is f prime of x, and let's just write that out. We say this f prime of x. Okay. Now, I know some of you in here have already taken calculus before, had some experience with it. What are some other ways that you've seen people write derivative? Every person kind of like picks their favorite way. Every textbook has a different way, but what are some other ways that we've seen notation wise that say derivative? Good. So one way to say it might be d dx, and that usually comes with a function next to it. All right. So d dx does mean derivative. What are some other symbols we've seen before? Anyone ever see this before? Okay, I've not typically used the capital D, which is not to say that that's not a thing. It's potentially a thing, but y prime is also a thing, right? So whoops, y prime is another way of saying find the derivative. Okay. How about this one? dy dx. Anyone ever see that one before? Okay. All right. So these are some of the more common ways that I've seen sort of across textbooks and different instructors on how to write find a derivative. Okay. So anytime you see any of these, and I'm going to try in the beginning at least to really do them all in different ways. So we get used to saying f prime, what is that? Oh, that means find a derivative, or dy dx. Oh yeah, that means find a derivative. Okay. So this last one here, we typically read this dy dx. Okay. I have heard a small percentage of folks call this dy over dx. I think actually there's one of my colleagues in the math department here says dy over dx. I've never said it that way. I used to joke that only the cool kids call it dy dx. Everybody else who doesn't actually know the math calls it dy over dx, but he actually knows a lot of math, so I felt really bad about saying that. So dy dx or dy over dx is fine, but all of these are just different symbols to help us say find that derivative. And when we're finding the derivative, what is it that we're actually finding? That's an actual question for you. When we're finding a derivative, what are we actually finding? Yes, and then almost. All right, so yes, the derivative we want to say is the same as slope. The derivative, though, maybe not our average rate of change. What is our derivative actually? Yeah, it's actually our instantaneous rate of change. Okay, instantaneous because like Vincent was saying yesterday, it's at that single point. And so when we're looking at a picture like this and we're picking specific points and finding that derivative or that rate of change at that point, we're actually finding the instantaneous rate of change. Okay, so maybe that's worth writing down as well, that a derivative is slope at a point or instantaneous rate of change. Okay, so a derivative is slope at a point or instantaneous rate of change. We have a picture to go with it, and we have some symbols that we're going to be using quite a bit. All right, so we ready to jump into some computation? Yay. Okay. So first rule up is the power rule. It is like the most commonly used rule, I think. And so let's take a look at this particular example. Okay, so this says f of x is x squared. And the question is f prime of x equals question mark. And so it would be important for us to say like f prime of x is really saying f prime of x, which is another way I could write this would be dy dx, or I could say find the instantaneous rate of change of this particular function. And here's how we do this if we're using the power rule. Okay, so f prime of x. What is the coefficient for the x squared? Correct. So that coefficient is 1. I'm going to keep that there. Times what's the power for the polynomial? 2. Okay, so I'm going to bring that power down. I'm going to keep the letter, and then I'm going to take the power minus 1. Okay, so let me say that one more time. I kept the coefficient. I brought the power down, and then I subtracted 1 from the power. So if I were taking notes, I might do this. Keep coefficient, bring power down, subtract 1 from the power. Okay. I won't always sort of annotate the formula this way, but I think that as a student, it's probably helpful to do that for your own sake, okay? And as you kind of go through other people's notes, maybe not in this class, but in future classes, annotating that can often help you connect the dots between how did they get from this line to this line, okay? I love the questions in the chat. When we are finding the derivative and we're using the power rule, we will always subtract 1, okay? So even though the numbers might change, this process, keep the coefficient, bring the power down, subtract 1 from the power, those 3 pieces will be the same every time you use power rule. Okay. Catherine, does that answer your question? Great. Okay. Is the 1 from the coefficient, or will we always be subtracting by 1? Okay, so this 1 is different from that 1. In fact, this 1 is just the invisible coefficient that we have from here. So if we had a coefficient of 5, then we would keep this as a 5. If our original coefficient was a 10, we would keep this as a 10. Does that make sense? Can we only use this when x has a degree of 2 or more? Excellent questions. Okay, so let's finish this problem before we get to the actual rule. Okay, so once we simplify this, and I know it's a little bit hard to read under all of this, but once I simplify this, what do I actually get? (2x). Okay, so I simplify, I get 2x. And so my answer, I'll just write this a little bit more neatly here. My answer would be f prime of x equals 2x. Okay. What does this 2x mean? Okay, what does this 2x mean? Here's what it means. This 2x means the slope at any point on x squared. Okay, the slope at any point on x squared is 2x. Now, I think a lot of calculus instructors, they want you to know the power rule. I want you to know the power rule too. Okay, so I'm not saying I don't want you to know the power rule. But in addition to that, I want us to be really thoughtful about what our answer means. Okay, that the slope at any point on my function x squared is going to be my derivative, or 2x. Okay. Now, folks are asking some really excellent questions, okay? I love these questions like, is it always like this? Or how do we know? Or can we use it for this case? And so this little blurb in the blue here is, I think, actually pretty helpful, okay? So let's read this out. If f of x is x to some power of n, then f prime of x is n x to the n minus 1. Another way to write that, instead of f prime, we're using our d dx notation, okay? Different notation, but same idea. If you like to write it with the d dx of your x to the n, you're still going to have n x to the power of n minus 1. And in this case, it's important to note that n is any number, all right? Now, this formula is sometimes called the power rule. All we are doing here is bringing the original exponent down in the front and multiplying, and then subtracting 1 from the original exponent. This next part, I want to highlight a couple things, okay? Folks, I love the questions that people are asking, like, can I always use it here? But one question I think is also important is, when can I not use a rule? Okay, so just like we say, when do we know when to use something? We also want to know, when can we not use something? And in this case, I want to make this really clear that in order to use this formula, n has to be a number. It cannot be a variable, okay? And the base x must be a variable. It can't be a number, okay? And the reason why I want to point this out right now is because next week, we're going to learn a case that looks kind of similar to this, but the rule is going to be different because we don't have a variable in the base and a number in the exponent. Okay. Now, let me ask you something. The way that the wording is in the blue, is that something that we feel like is readable for us? Because I know sometimes math books are like, it's like just a lot of words and symbols, and it's really hard to read. Okay, so if you like this, I know I talked about this resource on the first day. But I do want to redrop a chat in the link for this, okay? So I know a lot of times, especially in this day and age, we really like to watch videos and have people explain things. And I think that's such a powerful thing, okay? I think also, though, it's helpful if we can find math books or explanations that are easier to read, okay? And I will say that I think that the resource that I just dropped in the chat has a lot of easy to read things. And in fact, this blue blurb came from some of his notes, okay? So if you like this kind of style, then you might bookmark his particular page so you can go back to it, especially as we get into more and more rules. He has so many worked out examples that might be really helpful for you, okay? All right, I see a question. What about the coefficient being brought down? So by definition, a coefficient is already in front of it. What do you mean by the coefficient being brought down? Because there's actually the power that's being brought down. Oh, okay, I see, I see. Let me rewrite f of x for a moment, this particular f of x. If I write it, there is an invisible 1 in the front, yeah? Like x squared is the same as 1x squared. This 1 is this 1. Ah, okay, okay. So like, where is this idea coming from? Is that the question? Yes. So if you notice in this one, that coefficient is also 1. And so a lot of times when folks are introducing the power rule, we kind of say, oh, let's just look at when the coefficient is 1, and then we don't really talk about it. But later on, we are going to have different coefficients. So I'm just trying to like plant the seed of like what happens if we have a coefficient. Does that make sense? I'm sorry if it was more confusing in the interim. Okay, if we sort of ignore this part for a little bit, are we okay with the bring a power down and subtract 1 from the power? Okay, so let's maybe ignore the yellow part for a little bit. Maybe that's too much, too early, too soon, okay? But the basic power rule is this part. Okay, bring the power down, subtract a power. Yes, and so we're going to talk about that in a little bit. What happens when this number is not just 1? Okay, what happens when this number is not just 1? I just wanted to point that out. I'm sorry if that brought more confusion. If it's confusing, let's just ignore this for the next like 5 minutes. Let's practice some regular power rule, and then let's come back and talk about what that coefficient works. Okay. All right. So let's start off with example number 2. Okay. So if I want to find the derivative, my function is x to the 6th. The rule says we bring the power down, we keep our variable, and we lose 1 from the power. And so in this case, our solution will be 6x to the 5th. Exactly, Sherwin. Okay, 6x to the 5th. Now, what does that mean? That means that if I want to find the slope at any point on x to the 6th, I can just plug in that number, whatever my x value is, into 6x to the 5th, and that will give me the slope at that point. Okay. Now, I think this is very clear to see. This is so much faster than the formal definition, right? Can you imagine having to FOIL out 6 times and then make sure it's like an x plus h and then all that other stuff, and then hopefully you don't make any sign mistakes, and at the end everything cancels and you get 6x to the 5th. Okay, so this is very clearly a shortcut, but sometimes it doesn't feel quite so much like that, so I just want to highlight a few other cases here. Okay, so let's go over to example 3. I have d dx of pi. Okay, so d dx, another way of saying find a derivative, find the derivative of pi. Okay, so what are our thoughts here? D dx of pi. Ooh, I love this. Answers and questions. All right, so let's go back and read that rule. In order to use the rule, n must be a number. It can't be a variable. and x, the base, must be a variable. So Matt asked a really important question. Where's the x? Right? Where is the x? And so a lot of times when we don't see the variable we're looking for, we need to imagine what is invisible there. And so another way to write this might be like this: pi times x to what power? Okay, it is not x to the first power, because if it's x to the first power, we would see an x here. We don't see it, so it's x to the 0 power, okay? Now we can use the power rule. What is the power that we're bringing down? Power we're bringing down is 0. So we really have keep the coefficient times bring the power down, x to the power minus 1. Now we are following the rule. What does this give us if we multiply it out? Yeah, it gives us 0. Okay. So let's kind of look at example 2 versus example 3 right now for a moment. It is so important that you are able to find the power of x. You have to be able to see the power, okay? If the power was 1, you would bring the power down, you would lose a power. You could still use it if the power is 1. Okay, but the question would have looked different. It wouldn't just be pi, it would be pi x. Okay. All right, well, we're going to talk about this on the next page. We'll talk about some specific like sort of common scenarios, but I'm wondering if you could tell me right now, you know I love the pictures. How could we do this without a picture? The function pi is about 3.14, right? If I graph y equals pi, what does that look like? It's a horizontal line, right? When I say find a derivative, what am I asking you to find again? I'm asking you to find the slope, right? If I say find a derivative, I'm saying I want you to tell me the slope of that function at any point. And if we look at this picture, slope of a horizontal line is 0. That's why when we have just a number here, we actually end up with a derivative of 0. Okay, so to answer your question, Matt, where did it go? Will that be true of all functions where x is to the power of 0? If it's a constant, like pi, then yes, you will have a horizontal line, which means a slope of 0. Okay. I see a question that I missed in there. So if there's no x, then the derivative will always be 0. If you look and there's no x in the entire thing, that does mean x to the 0. And so, yeah, you'll end up with that 0. Okay.
Should they always show work?
Sorry, go ahead.
Should they always show work Because it's that easy, like x to the 0, it's always 0. Can I skip the work and just saying the derivative is equal to 0?
Yes, we're going to start to skip some work, and I'll try and be really explicit about where I want you to show work and where I don't want you to. Okay?
Okay, thank you.
Great. All right. Now, I really like to start off with the complicated examples because everyone knows how to do this one. Everyone knows how to do example 2, but that's not where people get confused. People get confused about 3, 4, 6, 5. Those are the ones that are confusing. So I want to make sure we can take a look at all these sort of special cases. Okay. So earlier this week on Monday, I said, hey, I want you to practice fractions and radicals and exponents. And here's why. Okay. The reason I want us to do this is because a lot of the calculus involves rewriting things using algebra. And so I want that foundation to be really strong for us. Okay. So I see this y equals the square root of x. Now, before I use that power rule, I have to see the power, just like I did in example 3. And so folks in the chat are absolutely correct. We're going to rewrite this as y equals x to the 1/2. Now, I want to make something really explicit here. Some folks on the assignment, the fractions and exponents assignments, missed this. The power of x here is 1. That's where this top 1 comes from. But when we see this symbol, we say a square root, there is an invisible 2 there that we need to know about. And that is where that bottom 2 comes from. Okay. So being able to go back and forth from square root to x to a power is so, so, so important. Okay. But once we see that, now we can apply the power rule. Y prime means I keep my coefficient of 1. I'm going to bring the power down, x to the 1/2 minus 1. Yes, so the cube root would be x to the 1/3 power, precisely. Good, okay. So what else did I ask you to do on that fractions and exponents? I was like, could you just do some like 1/2 minus 1, 1/3 minus 1, 2/3 minus 1, and everything was minus 1, because for the next few weeks when we do all these derivatives, we're going to be subtracting 1 a lot. And so I want us to make sure we remember how to do that. And so if we, let's actually maybe write this over here. If we have our derivative and now we simplify, we're going to get 1/2 x to the power of, I think I see it in the chat already, -1/2. All right, so I just want to pause right here for a moment. Are we okay with the power rule and this first line of simplification? You can give a quick thumbs up or a yes or no. All right, I see some thumbs up. You don't have to turn the 1 into 2/2, but if you tend to subtract fractions wrong, I would take that extra step, okay? So this is all fine and good, but I bet in a lot of answer keys, you won't see your answer that way. And there was another part of Monday's assignment where I asked us to rewrite some things so that we could almost get to a place where there's positive exponents and no fractional exponents. And so if I think about how I might be able to write this, I could say 1/2 times 1/x to the positive 1/2. Does that make sense? How I got from that second line to the third line? Yes, okay. One last thing to change, because again, I don't think this is going to be an answer in a textbook, is we're going to combine these into one fraction and we're going to turn that x to the 1/2 into the square root, like Sophia said. So 1/2 root x. Okay. So that means that if I want to find the slope of the square root function, I can say the slope of that square root function is always going to be 1/2 root x. Okay, 1/2 root x. All right, let's take a look at number 5. Ooh, some more fractions. So this first step right here, is this what you're talking about? Oh, the next two. This one? Like, how did this come to be? Sorry. Okay. Where did this come from? Is that what you're asking? Okay. Thank you. Thanks for your patience. Okay. So where did that come from? Let's do a little bit of color coding to help us out here. 1/2 is still this 1/2. Are we okay with that part? And then this next part, right, x to the negative 1/2, what do we know about negative exponents? If we want to write them as positive exponents, we bring them to the other side of the fraction line. So 1/x to the 1/2. Yeah, there we go. Okay, and then the last step, this square root of x on the bottom is the same as 1/x to the 1/2. Yes, yes, Luca. And if the negative exponent is in the denominator, it goes up to the numerator. Exactly, exactly. Okay. All right. Let's take a look at example 5. All right. So we've got f of x equals -3/x to the 4th. How do I rewrite this? What is another way of writing that? Good, -3x to the -4. Okay. If you do not rewrite, I guarantee you're going to get these questions wrong. Okay. This is where that algebra piece comes in. If this part is not very strong for you, it makes this part impossible. And that's sad. Okay. Because you've worked so hard to get to this point. If this is not feeling very strong for you, you have a worksheet, you can make up other examples. I would practice a bunch of them. Okay. All right, so now we've rewritten our original function. So our f prime of x, I'm going to keep the coefficient there. Okay. Now I'm going to bring down the coefficient, or the power rather. So -4x to the -4 minus 1. Are there any questions about how I got this first line here? Okay. No questions on that. Now let's simplify. -3 times -4 will give me a +12. And x to what power? X to that -5 power. Okay. So earlier, I know folks had said like, oh, do you want us to write out that step? In this case, I can't tell you how many students I have who, if they don't write this out, they end up with a -3 here. I don't want that to happen to you. So if the negative exponents in the beginning, maybe just take some time to write it out so that you make good habits in your brain about what that number is actually supposed to be. Okay. In other words, I feel very not bad for you if you do not write this out and you get the wrong answer here. Okay. So last step, we practiced rewriting these on Monday as well, and we'll get 12 over x to the 5th. Now this would be an answer probably in a text, whereas this is less likely to be an answer. Okay. So let's take a look at 4 and 5. Are there any questions on 4 and 5 so far? (12x to the -5). No, that's why I'm boxing this answer. I want us to write it this way. Okay. And here's why. I find that if you only know how to get to here, but you cannot get to here, there's probably some algebra that you need to practice. So I'm gonna make you practice that. Okay. As we get into integrals and sort of the second half of the class, we're going to be a little bit less picky about what needs to be simplified. But for derivatives, I think this is more conventional to have the answer this way. Okay. Cool. Thank you. Do we want us to write our final answer as a fraction? Yes, I don't want to see negative exponents. Okay. No negative exponents, no negative exponents. So if that means that it has to be a fraction, then so be it. All right. Cool. Another way to think about that is, how was the question asked? So this question was asked as a radical. You should probably get your answer back into that same form. This question was asked as a fraction. Your final answer should probably match that same form. Okay. But so much of this, especially for folks who are going on to Calc 2, this kind of algebra is like, Calc 2 is so algebra heavy. I want us to feel prepared, not just in the calculus, but also for the algebra when we get to that next course, if we go to that next course. Okay. All right. One last one before we go on break. And let's take a look at something that, ooh, maybe worst nightmare for some of us, but it combines all those things. It combines negative exponents. It contains radicals, and we want to be able to rewrite that all. Okay. So let's start with an alternative way of writing f of x. And it is indeed, let's see, if we break this up piece by piece, 2 over x to the 2/3. So that's another way of writing that. But we want to make sure that we don't have a fraction, but we can actually see the power 2x to the -2/3. The 2 and the 3, neither of those are making it negative. What's making it negative? Anybody else know what's making this negative?
The fact that it's on the denominator.
Yeah, we're moving it.
Exactly. Does that make sense, Vincent? Yeah, like the fact that this is down here is what makes that a negative sign. Yeah, I know. I feel like individually, like in example 4, it's okay. In example 5, it's okay. But example 6, it's like you're throwing it all together. You really have to know the different rules there. Okay. So thank you for asking that. I'm sure a lot of folks had that question, like what part of that makes it negative? Okay. All right. So now that we see our power, let's go ahead and apply our power rule. So we're going to keep our coefficient. All right. And let's bring down our power. And we're going to subtract a power. All right. Now you'll notice that I tend to put my parentheses in more often than not. If I remove these for a moment, I've definitely seen some students who write it like this, and then all of a sudden they're subtracting those powers in the front instead of multiplying. So that's why I like to put the parentheses there, right? We don't want to leave ourselves a trail of unuseful breadcrumbs. We want to be really helpful to ourselves about how to move forward. All right. Let's do a little bit of multiplication here. 2 times -2/3 is going to give me -4/3. And x to the -5/3. Good, good, good. Okay. Now, this is all fine and good. The calculus part is done. However, based on the way the question was asked, right? We want to make sure we match that question format. So let's see how we might rewrite this. I'm going to rewrite this as -4/3 times. Let's undo the negative part first. So 1 over x to the 5/3. Okay. And the last step, x to the 5/3, if I rewrite that as a radical, I will end up with the cube root of x to the 5th. Okay. And in particular, this 4 and 3 are still those 4 and 3. But this x to the 5/3 is this cube root of x to the 5th. All right. Let's box that off so we know that's the final answer. And how are we feeling about that particular question? All right, I know it layers on example 4 and 5 together. All right. Well, if you have some questions that come up during the break, you are welcome to ask when we return from the break. But I think now seems like a great time for a break. So take a break. Back at 8:15 a.m. We will go through some rules that I think we've already talked a little bit about, and then we will learn more rules that are all shortcuts for that formal definition, okay? So I'll see you folks back here in just a little bit. All right, folks, welcome back. Before we move on, I wanted to see if there were any questions about any of the examples we've seen so far. We're getting some really great questions today. So just wanted to see if there were any more that folks had thought about over the break. And if not, we'll move along. And if other questions come up, then we can certainly address those. Question 3, yes, what is your question about example 3?
Yeah, do you use cross multiplication? Like how do you get the pi times x to the power of 0?
So anytime you don't see an x, there is an invisible x there, but it is to the power of 0. Okay, so this is a definition.
Mm-hmm.
Yeah.
Oh.
So there's no cross multiplication. It's just that x to the 0 is there invisibly when we don't see an x. Okay. That is one of the tough things about math. There's so many invisible numbers, right? And similarly over here, like there was sort of an invisible 2 and an invisible 1 that we had to write out there. So those are things that I'll try and make really apparent as we move through the different questions, okay? I know it's a lot to be like, oh, there's secretly a 2 here, there's secretly a 1 here, there's secretly a 0 here. So we'll try and keep track of those. All right, so I do want to talk about 2 special cases of the power rule, okay? And so in particular, one of them we've already kind of taken a look at. Some textbooks give this a different name. They call it the constant rule. Okay, so that might be the name of a rule that you see it called somewhere else. And the rule goes something like this. If I take the derivative of a constant, so C is a constant, then we will get 0. And that's how the rule is typically presented, okay? But actually, let's make a note here. C is just a number. Now, I want to be really clear here. Is C being multiplied by anything else right now?
No.
No, it's not being multiplied. It's literally just a number. Like literally we had just pi, okay? So if we have a derivative of a number, it's going to be 0. But the reason why is, if we think about what we wrote before, next to the C, there was an invisible x to the 0. And so when we use the power rule, we get C times 0, x to the 0 minus 1, which gives us 0. So this longer line shows us why that derivative is just a 0, okay? But the other thing we talked about is that C, so y equals C is just a horizontal line. All horizontal lines have a slope of 0. Okay. So we can think about it just as a rule, right? But I think we all know that sometimes when we only memorize the rule and we don't understand why, or we don't understand when to use it, we get in a lot of trouble. And so the last 2 pieces, all right, so sort of the longer way of saying this with that invisible variable present, and thinking about it graphically are sort of 2 ways to help us really understand why that rule works the way it works, okay? There's another special case of the power rule. Some textbooks and some instructors actually give it a name. Oftentimes we call it the linear rule. Okay, so a constant rule and a linear rule. And at the very basic linear function, we really have something that looks like this: C times X, like a number times X. And the rule says that the derivative of C times X is C. Okay, that's what the rule says if you look it up. C, just like before, is just a number. Okay. But what I'd like to do is to write 2 similar pieces for the linear rule that we did for the constant rule. Okay. So I have my d dx, C, x to the, what's the invisible number that would be really helpful to write out here? Exactly. So this has a power of 1. Okay. This has a power of 1. Now, if we use our power rule, we're going to get c times, bring the power down, x to the 1 minus 1. C times 1 gives you c, and this is x to what power after we use the power rule? C to the, or x to the 0, good. What is x to the 0? Oh, there you go. X to the 0 is equivalent to 1. And so we end up with C. Okay, so we could use the power rule. It's not that we can't use the power rule. It's just that this happens so often that we sometimes give it its own rule. Okay, but that's why we get just a slope or a derivative of C. But let's think about it as a graph. Okay, so y equals cx is a linear function with a slope of, what is the slope of the line y equals cx? Yeah, Joey, it's only c, right? The slope here is c. Therefore, the derivative of y equals cx is c. All right. Remember, derivative is the fancy way of saying find the slope of this function. And if the slope is always 0, that's when we have the horizontal line. But if we have like a regular slanted line, the slope is just the coefficient of that linear term. Okay. So some folks teach this as separate rules, but I wanted to bring them back to the idea of the power rule because they're all power rule. It's just that they happen so often that it's not worth writing out all this work. Instead, we want to know when we have just a number, that derivative is 0. But when we have a number times x, that derivative is the number. Okay. All right, let's take a look at this. Whoops, let's take a look at this sum and difference rules. Okay, so sum and difference rules. Light blue, I grabbed this from Paul's online notes again. I think that he did a great job of explaining it, but I also want us to get used to reading from different sources, right? And not just relying only on listening, but also being able to read. And so it turns out that when we are adding or subtracting, and this is super important here, when we are adding and subtracting, adding and subtracting, adding and subtracting, okay? Notice I did not say multiplication and I did not say division. So when we are adding or subtracting, you can actually do it piece by piece, find the derivative piece by piece, and then add or subtract everything back together, okay? This is not going to be true for multiplication and division. We will have special rules for multiplication and division, okay? So let's take a look at an example here. We've got this, y equals x to the 8th plus the 5th root of x squared minus 5x. I want us to find y prime. And so my suggestion before you even begin the calculus part is to start with some algebra. And in particular, I encourage you to rewrite a question so that you can see all of the powers and no fractions. So if I rewrite this equation, I'll get y equals, let's see, x to the 8th does not change, but here I get x to what power for that middle term? X to the 2/5, good, 2/5, minus 5x to what power for the last term? -1, good, good, good. Okay, so that first line, no calculus, just the algebra. Now we do the calculus. We're gonna find y prime. Okay, so y prime equals, what does the first term become? Just the first term. If I have x to the 8th and I take that derivative, what does that become? 8x to the 7th. Okay, so we're going to bring that power down, 8. Keep that x, and 8 minus 7, or 8 minus 1 gives you 7. Okay. Plus, let's take a look at the second term, x to the 2/5. If we use power rule here, what derivative do we get for the second term?
Two over 5x to the -3/5.
Good, good, good. All right, last one. What do I get when I take the derivative of that last term?
Plus 6x to the -2.
Ooh, let's see. So I have a -5. I'm going to keep that in front. I'm going to bring that power down. -1 x to the -1 minus 1. Okay. Got to put those parentheses in there. We want to make sure that we can simplify appropriately. All right, so we're actually going to do that as a third step. Now we're going to simplify. So y prime equals, first term stays 8x to the 7th. That's fine. Plus, that's middle term 2 over 5, the 5th root of x cubed. Okay. What is the coefficient for this last term though? It's not 6. It's going to be 5. Yeah, it's going to be 5. So -5 times -1 gives me a +5. And this is x to the -2. So let's take one more line to simplify that. And obtain our final answer. Okay. So let me pause here for a moment. All right, I know there was calculus in that middle line, but there was also a lot of algebra around that. So let me take a moment and pause and see if there are any questions that are coming up. How did we know which power of x to use from the original equation? Are you talking about the rewrite step? Like, how do you know when to rewrite things?
Once we rewrite it, we have x to the 8 and x to the -1. So you you only really did a manipulations with the power rule for the -5 x to the -1. Could you have just chosen to do that on the x to the 8 or the x to the 2/5 instead? Or
Oh, we did it
why
on
did you?
all of them.
Oh, I know, I do see that. I'm sorry.
Yeah,
I'm
you're
sorry.
fine. Nope, you're absolutely fine. So that is the whole idea behind the sum and difference rule. You can just do each one as sort of a mini problem and then string them all together. Okay,
Thanks for clarifying.
of course. All right, let's try one more example. Example 8. All right, I see some square roots, I see some fractions, and I'm thinking I better be able to find that power. Okay, so f of x, how do I rewrite that square root of x? Good, x to the 1/2 plus, how do I rewrite the second term so that I actually see no fractions? Good, 2x to the -8. All right, let me ask you folks a question. Have we done calculus yet? As in, have we taken our derivative? No, we have not. Okay. And I think sometimes we're so used to things being like a one-step thing that if we rewrite something, then we're like, oh, I must be done. All right. But this is just sort of the prep work to make the rest of our lives easier when we find our derivative. Okay. So f prime of x. Let's get that power rule for the first term. We're going to bring that power down, x to the 1/2 minus 1. Right. So I've used the power rule on the first term, plus 2 times -8 x to the -8 minus 1. Okay. Now, have I done calculus? Okay, now we've done the calculus. And to finish things up, we are going to simplify. I'm going to break this up into 2 separate steps in case there are some of us in here who are secretly like very lost about the simplification, but we just don't want to ask. Okay. So this 1/2 in the front, I'm going to keep as 1/2. And then I have x to the -1/2. So that's 1 over x to the 1/2. Minus 2 times -8 will give me that -16 x to the -9. So that's sort of a first step. And then we'll be able to get the same answer as in the chat, which is 1 over 2 square root x minus 16 over x to the 9th. Okay. I know we haven't even taken exam 1 yet, but questions like example 8 and questions like example 7 are pretty much guaranteed to be on exam 2. Okay, so being able to work not just in the x to the 8th case, I know we can all do that. I want to know, can we do it when we have fractional exponents, negative exponents, or sort of both negative and fractional exponents, okay? I'm glad that you are having fun with the power rule. Things are about to get a little bit more complicated, so buckle up and let's take a look at this product rule, okay? So earlier I said, hey, you know, when we're adding and subtracting, we can just take all the derivatives and then string them all back together. All is fine and good, okay? However, when we are multiplying, that is not the case, okay? I cannot stress this enough. when you are multiplying if you don't use the product rule, you're not doing it correctly. Okay. And that is so sad to see when people see the product of two things and then just take each derivative and then call it a day. Okay. I don't want us to do that. You will be sad too. I promise you will be sad. I don't want you to be sad. Okay. So product rule, we're going to use when two functions are being multiplied. And Johanna, where does that 1/2 coefficient come from? Maybe we can use that answer to answer your question. Like, where does this 1/2 come from? Yeah, it's from that power. So if the power is 1/2 and you take a derivative, then that coefficient should be 1/2. Okay. Okay. All right. So we've got this product rule. Some of you know this rule, others of you do not. But I have this question, y equals x cubed times x to the 4th. And I'm telling you that even though you don't know that product rule right now, we can actually take that derivative. So what are some ideas on how we could find this derivative without this product rule that Judy just made a really big deal about? Sum of the exponents. Oh, okay. So I wonder if we borrow from our previous question where we rewrote it, we took the derivative, and then we simplified, if that might help us out. So let's rewrite. Y equals x to the 7th. Okay. Now I'm wondering if we could pause here for a moment, because exponents and their rules are oftentimes confusing for folks. How come it's x to the 7th and not x to the 12th, right? That would be another answer I could see people. Okay, but how do we know we're adding them here? Like, what about this tells us that we should be adding and not multiplying? When would I multiply? Like, what would it look like if I wanted us to get x to the 12th? Yeah. Like a power to a power. Okay. So maybe let's jot that down over here, that x to the 3rd times x to the 4th equals x to the 3 plus 4. And x to the 3rd to the 4th is x to the 3 times 4. Okay. So I think these two rules oftentimes get confused. And so we want to make sure that we know what that strategy is. I really like what Sherwin put in the chat. So if you haven't looked at that chat, I came in around 8:40. All right. He wrote it as x times 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 x. And if you look at how many x's there are 7 of them. So it's x to the 7th power. Okay. But once we've rewritten them, let's find our derivative. And so you'll see here I'm using dy dx, right? Trying to use all the different notations so we get familiar with all of them. And so dy dx will equal what? Seven. All right, so bring that power down. X to the 7 minus 1, which is 6. Good, good, good. Okay. We don't have to simplify here. So there we are. There's our answer. Okay. But what I'm going to do in the second box over here is I'm going to use the product rule. So we're actually going to do the product rule first before we look at the definition. Okay. And it's going to be more complicated in this case. Like if I saw this question on a test and it didn't tell me which method to use, I would 100% use the method we just used. However, the more we learn, the more we're going to get to situations where we may not be able to simplify this. And when we can't simplify it, we will be forced to use the product rule. Okay. So it's really important that we understand the product rule and when we can use it and when we can't, when it might be faster and when it might not be faster. Okay. So here's what I'm going to do. I'm going to set up the product rule here. So I'm going to let u equal x cubed and v equal x to the 4th. And so if I go back to my original problem, I'm going to see that x cubed is my u, okay? And that x to the 4th is just, I'm going to call it v. All right. Now, what I'm going to do is find du, which is the derivative of u, and I'm also going to find dv. So can you folks help me with that? What is the derivative of x cubed and what is the derivative of x to the 4th? All right, I see one answer there. 3x squared, good. And thank you, 4x cubed. All right. So I'm going to find those 4 things. Okay, I'm going to find those 4 things. And now I'm going to plug things into the product rule. y dx equals u dv plus v du. Right, u dv plus v du. And all I'm going to do is plug in all the stuff that I just set up. So x cubed times 4x cubed plus x to the 4th times 3x squared. Okay. Are there any questions about where I got the terms from? Like,
why did you do UDV and then VDU and not like UDU?
great question. Hold on to that question. Are there questions about the process right now? Like how I put those numbers or where those terms came from? Or are we okay with that? Okay. So now if we simplify, look at what we get. The first term becomes 4x to the 6th. The second term becomes 3x to the 6th. Now, I know we're doing a lot of higher level math here, but this is really 4 of something plus 3 of that same something gets you the same answer. Okay. Now, as I said before, I think the first way in this particular problem is 100% easier. And if I was not told use a specific method, I would use the first method. Okay. However, as we move into like quiz 4, I do want us to practice setting up that product rule when we need to, okay? So because we're going to use product rule a lot in cases where we can't do this first way, it is important for us to sort of practice this setup, all right? Now, the most fabulous question, but why did I plug it into this formula, okay? And so it turns out that if you have two functions where you can find the derivative, then we can write that product rule like this, okay? And so this is the same thing as what we set up here, but just using slightly different letters, okay? So I just want to unpack this for a moment. So in this case, I have, instead of U and V, I have F and I have G, okay? How do I write the derivative of F using symbols? How do I write the derivative of F using symbols? I could say df. I could say F prime, good, right? And so if we look at the notation over here, it seems like maybe we should use F prime, okay? So similarly, then the derivative of G is going to be G prime. Now, we will see that when we use this product rule, okay, that we've got, I had put U dv. How would I write U dv using these letters here? I think it'd be like F G prime, right? F G prime would be the same as U dv. Okay, so Fg prime equals Fg prime plus, how would I say V du? I would say G F prime. Okay. Now, at first glance, what I just wrote looks very different from the formula they gave. And this point often causes students a lot of confusion. They're like, I followed the formula. How come your formula is different? Okay. But I wonder, yes, they are equivalent expressions. Now, how do we know that they're equivalent? What's 2 times 3? Yeah, 2 times 3 is 6. And what's 3 times 2? Also 6, right? So when we multiply, does the order matter? Exactly, right? So just like Sophia said, the order does not matter when you're multiplying. And so if I write Fg prime and I have that over there, that's fine, right? But F prime G is actually the same as GF prime. So that in that case, the order doesn't matter. But also, let's think about 2 plus 3. That gives us 5, but so does 3 plus 2. That also gives us 5. So when we add and when we multiply, the order doesn't matter. And so that's why some folks might write this in a different order. And that would be okay. All right. As long as you are essentially taking one function, multiplying it by the derivative of the other, and then adding it to the second function times the derivative of the first, then you're good to go. Okay. All right. Here's what I'm going to do. So this next part, all right, maybe better addresses the question of why the formula is the way it is. I will not ask you to derive this formula. This is more for a like personal satisfaction of, oh, this is where that rule came from, okay? So I'm going to use the formal definition of the derivative here to prove this rule. All right, so I'm going to start off with the limit h approaches 0 of f of x plus h times g of x plus h. So this is my f of and g, but with x plus h put into it, minus f of x, g of x, all over h. Okay. So all I'm doing is saying I have f of x times g of x. I'm going to plug in x plus h, and I'm going to plug in x, and then I'm going to subtract those two. Okay. Are we okay so far with this setup? We're looking at product rule. All right. So one fancy trick that we often use in mathematics is we like to add 0 to things, because when we add 0, it doesn't actually change anything. But what that allows us to do is be really clever in the way that we add 0. So I'm going to stick a 0 in the middle of this. And this in particular, the 0 will be as follows. Minus f of x plus h g of x. Now, if I subtract this, what do I need to do in order to keep the purple part equal to 0? I have to add it as well. So plus f of x plus h g of x. Right? So I've got this purple thing here that's now made my problem more longer, but it's just 0. So I haven't changed anything. Okay. Now I'm going to group some terms. And in particular, I'm going to split this fraction into 2 separate fractions. So I'm going to sort of divide along this way. So, whoops. I'll get the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x plus h, g of x, all over h. That's the first fraction. Okay. And the second fraction will be f of x plus h, g of x, minus f of x, g of x, all over h. Okay. So I started with the definition, I added 0 in a very fancy way, and then I split this into 2 fractions. Okay. Let's focus on this first fraction. What is the greatest common factor there? Excellent, excellent. Right, so let's kind of highlight that there. I see f of x plus h in both terms. Okay, now tell me about the second fraction. Common factor is g of x, right? Okay, so I'm going to factor the f of x plus h from the first fraction and the g of x from the second fraction. Where did the purple come from? That is my fancy way of saying let's add 0. Okay, so it's a clever way of adding 0 so that we can prove our power rule. Okay. That's my greatest common factor there. Second one, I'm going to bring that g of x to the front. Because if I had this over h as well, when I multiply, that'll give me like h squared. Right? F of x plus h is really f of x plus h over 1. So I'm choosing to keep the h with the g terms. I could also put it with the f of x plus h, but I could only put it with one of them, not both of them, because we're multiplying, right? If we were adding fractions, then we would need it over h, but since we're multiplying them, we only keep the denominator with one of them, okay? Yeah. All right, now here's the cool part, okay? How did I know to do this? This is the worst answer I can give you is experience. Okay, so how did someone know how to do this? Experience and perhaps a lot of trial and error. But what it allowed me to do, this right here, g of x plus h minus g of x over h. That's just a fancy way of saying g prime. Like that's the definition of the derivative of g of x. This is really g prime of x. And when I plug in 0 for f of x plus h, what do I get? I don't get 0. I'm plugging in 0 for what? Plugging 0 into f of x plus h. Right, so when I plug 0 into there, what do I get? Just f of x, right? So this is f of x. Okay. This term in the second one, g of x stays as g of x. How can I rewrite this second term? Good, f prime of x. So look at what we have. F of x, g prime of x, plus g of x, or f prime of x. All right. So this is the longer, more formal or rigorous way of saying this is where the product rule came from. Okay. It came from the formal definition. We did some clever algebra and we were able to arrive at a solution. Okay. And in particular, this formula takes us to our product rule. What about the blue? Can you be a little bit more specific? I'm happy to answer that. I'm just not really sure what your question is about the blue. How those fractions indicate g prime? Well, what if I ask you to write the derivative of g prime, like using the formal definition, it's the limit as h approaches 0. So this is from yesterday, right? Of g of x plus h minus g of x all over h. All right, so that is just from the formal definition, recognizing that format, and then turns out that's what popped out when we made our clever substitution. Does that make a little bit more sense about where the g prime came from? Yeah, okay, good, good, I'm glad. Yeah, so I think a lot of times when we think about proofs, we're like, oh, it's like so much writing, so much explaining. But it's actually pretty cool that like you can think about some ways all you did was add 0 and you were able to find out exactly where that formula came from. Okay. So take it for what you will. I will not ask you to do a proof like this on the exam. There's a whole nother course on that if you choose to go that way in the future, right? But in this particular case, I wanted to show you one to kind of see like, where do these formulas come from? We won't always do a proof, but I think it's nice to do it like a few times just to kind of see where some things come from, okay? Question for you folks. I know we normally take a second break. We are about in the last 20 minutes of class. So if we take like a 10-minute break, then we'll have like 10 minutes left. Are we okay pushing through today? Would we? I know, I'm sorry I didn't manage the time better. There were great questions on this. I didn't want to ignore them. All right. Okay, so I apologize for the lack of the second break, but I'd love to cover this example right here so that we can maybe think about what actually might get asked on an exam, okay? So I might ask you to differentiate, all right? So differentiate is another way of saying find the derivative, okay? So differentiate is another way of saying find the derivative. Okay. Now, because we just learned product rule, I'm going to ask us to practice using product rule here. However, you could also use FOIL to simplify this part and then just use the power rule. Okay, so I want to use the product rule here so we get at least one example worked out where we did the product rule. Okay, so how do I know, first of all, that I'm going to use the product rule? What indication do we have that we're using the product rule? No, we'll talk about simplification at the end, okay? All right, so I see the parentheses, I see the product of two terms, exactly. So I see something times something else, all right? And as soon as you see that, I want us to think product rule. And because this is our first example, let's write that out again. F prime of x will equal u dv plus v du, all right? And what we're going to do first is we're going to set up for our product rule, okay? So in particular, let's identify our u as the cube root of x minus 1. And we're going to identify our v as 2x minus x squared. Okay. But in order to find du, it would probably be beneficial for us to rewrite our u. Okay. So how do we rewrite this? We get x to the power of what? What is our power here?
1/3.
1/3, good. 1/3 and then a minus 1. All right, and I don't think that we need to rewrite anything for v, except we might want to put a friendly reminder to ourselves here that there's actually a power of 1 next to that x in 2x minus x squared. Okay. Now let's find our du and our dv. So du is going to be 1/3 x to the negative, to the 1/3 minus 1. And then minus, what is the derivative of 1? It is 0. Good, good, good. Okay. Now, I don't expect us to write a minus 0 every single time, right? However, if the longer we go in this class, the more you realize you forget that the derivative of 1 is 0, then I would encourage you to write it out for yourself. Okay, so if you're making those mistakes, then try a different strategy to fix that, okay? But let's see what this gives us. We get 1/3 x to the negative 2/3. And if we want to write that as a fraction with radicals, we'll get 1/3, the cube root of x squared. All right, dv I think is easier though. What do we have for our dv, or our derivative of 2x minus x squared? Looking at that derivative. All right, I see a 0 minus 2x. All right, any other thoughts?
2 minus
2 minus 2x? Ah, okay. So what are our thoughts? 0 minus 2x or 2 minus 2x? It looks like this part is still going to be the same, right? We know that that derivative of x squared is 2x. But if we take a look at 2x, and I want to take the derivative and I'm not sure, well, why don't I just write out the power rule? So 2, 1x to the 1 minus 0. Yeah, which is 2 minus 2x. Exactly, exactly. And also let's think about this, 2x. 2x is a line. What's the slope of that line? Well, that slope is just 2, okay? So that's another way to confirm for yourself if that's the proper derivative or not, okay? All right, second part, we are going to substitute into the product rule. Okay, so we've set everything up. Now we're going to substitute it in, and we're going to get f prime of x equals, let's see, our u was the cube root of x minus 1. dv is 2 minus 2x plus v is 2x minus x squared times du, which was 1/3 the cube root of x squared. And so this is our u dv and v du. All right, so all I've done is substitute that in. Now, I got a great question earlier about like how much we need to simplify here. This is as far as I would go for simplification, okay? No, cube root, please. All right, so let's get used to that fractional exponents, square root, cube root, like being able to go back and forth between those two. Really, really important. Okay, it's important now for derivatives, but it's going to be just as important when we get to integrals. So I'd really like us to have that be totally second nature for us. Okay.
Yes, I have a quick question.
Yes, absolutely.
Previously, where it says v equals 2x to the first power minus x squared, and then it says dv equals 2 and then 1x, so 1 minus 0. Why isn't it 1 minus 1?
I'm so sorry. That should say 1 minus 1.
Okay.
I was thinking 1 minus 1 is 0, and then I wrote 0 and not 1.
Okay, I was just making sure. I was like, oh no, I missed
No,
it.
no, no, you're good. You're good. Okay. All right. So as far as simplification, I do not need this to be a single fraction. And probably much to the dismay of some of your previous teachers, I don't need you to rationalize this denominator. Okay, so leave that denominator the way it is. Leave that as two separate terms. I don't need you to FOIL that out either, like the first two terms. Okay, there's so much of the more important algebra that you've already done here. I don't need to see how simple this can get. Okay. All right, so let's take a look at some special cases, and this will probably be okay, yep. So special case of the product rule, okay? So the special case of the product rule is sometimes called the constant multiple rule. Constant multiple rule, okay? And I think that we have already seen this rule, but what makes it so special is that we're not multiplying two different functions like something with an x, something else with an x, but it turns out that we are multiplying a number and a function, a number times a function, okay? And when it's just a number times a function, then we can effectively keep that constant out to the front and then take the derivative of the rest, okay? And so it's almost like, let's go back to all the places we've seen this, the derivative of 2x to the first. 2 is a constant, x is a function of x. So I kept the coefficient, then I did my derivative of the second function. I did not use product rule here. Okay. Where else have we seen this? Constant multiplied by a function of x. What did we do with that constant? We kept it out in the front, and then we did the derivative of the function of x. Constant is 5. Keep the constant, but take the derivative of the function. Okay. So yes and no. It does involve the power rule because that's the only rule we know right now, but it is in fact thinking about the idea that the constant can be any number, and therefore we can almost not worry about it until the very end. Like we can almost multiply it back in at the very end. Okay. But let's talk through these two examples first to kind of unpack like why that is the way it is. Okay. So what I'm telling you, I'm trying to convince you of is that in this case, the ddx of 5x, that I could take the 5 out to the front and then just do the derivative of x. That's what I'm trying to convince you of. And so this would give us 5 times, what's the derivative of x? That's 1. Good. Okay. And so 5 times 1 gives us 5, right? But if you were like, I don't know, 5 times x is the product, and she told us to always use product rule, then maybe you would set it up like this. U would be 5 and V would be x, right? If you wanted to use product rule. Oops, sorry. What is our du and what is our dv here? Like what's the derivative of 5 and what's the derivative of x? Yeah, derivative of 5 is 0. Derivative of x is 1. Okay, now let's plug this into our product rule. U dv plus v du. That's going to give us 5 times 1 plus x times 0. Right? Every time you use the product rule and one of your functions is a constant, that derivative is always going to be 0, which means one of those terms is going to go away, right? Anything times 0 is going to go away to 0. Because that's always going to happen with a constant, we have a special rule called the constant multiple rule. Okay, because it happens so often. And that's why if we go back up here, the derivative of 2x was 2, not 0. Okay. But let's see this maybe in a different example. So maybe example 12 over here. What is the coefficient that I would want us to pull out of this expression? Great, so let's take the 2 out to the front. I'm really asking you to find 2 times the derivative of 1 over x to the 9th. Okay. How do I rewrite that function? Perfect, so that I can see the actual power. 1 over x to the 9th is the same as x to the negative 9th. All right, let's use our power rule now. Negative 9, x to the negative 9 minus 1 will give us negative 10. And then this will give us negative 18 over x to the 10th. A lot of these rules, it's not that there's so many of them, it's just some of them come up so often that we're like, this is a good one to know. This is a shortcut, right? Because the more we layer on later, if we have a lot of these shortcuts at our disposal, it'll make some of those computations a lot easier. Okay. All right, so let me actually take a quick peek at quiz 4. But this is where we're going to stop in terms of content for today. Okay, so we're not going to get to the quotient rule today, and that is absolutely fine. All right, so update on quiz number 4. That is, please complete numbers 1 through 4. Okay, you can do all of those. Skip number 5. That will be what we learn on Monday next week. And skip number 6. Okay, those it was a very short quiz to begin with, so all you are doing for quiz number 4 is numbers 1 through 4. Okay. All right, so folks, that brings us to the end of today. Again, on Monday, we'll pick up with new content again, but for right now, we can sort of put all of this away so that we can prepare for that exam tomorrow. And quiz 3 you should be able to complete all of quiz 3. Okay, so quiz number 3 is completable. All right. All right, folks, I will be on Discord, so definitely send me a message if you're feeling stuck. If you haven't joined the server yet, it is not too late. I want to help you. I would rather help you than have work turned in where clearly you had questions, okay? So I'll see you folks later. Good luck. Please be on time tomorrow for the exam, and I will see you later.